Okay, so I'm just gonna randomly pick a couple because I don't have. Is there back there? I don't know. You have to go back and see, otherwise you just have to wing it. Okay. So here we go. Let's just start on the front page. So we'll use this first shape. So let's see if we get it copied correctly. So I've got a big triangle like that, and I've got a little triangle. And then over here, I've got a big long trapezoid. Okay, so that's my original. That's what I'm gonna use for all these. So just look on the front page, pick one. Which one would you like to do? Look at all of those variations. 7. All right, so 7. Okay, so what's happening here? Two things. We got this going on, and we got this going on. What does this do? No. When it's absolute value of just x, what change does that make? Absolute value of just x. Uh-oh, maybe you better look at your notes.
All parts.
No,
So everything on the bottom was the top.
no.
It's mirrored.
This is, you draw right and mirror left. Or mirror onto left, okay? So here's what I'm gonna do. I'm gonna draw whatever I see on the right side of my picture. So this is what I see on the right side of the picture. So I'm gonna draw that exactly as it is. So everything is just staying the same on the right side. So there is the right side of the picture. All right, then what? Take that and mirror it onto the left. So that exact same thing over here. There it is. So that is this right here. That's what this does. This takes what's on the right and draws it again exactly the same on the left. Okay, now what? I gotta get my attendance in before I get in trouble, like I did yesterday. Okay, so Tegan's out. And somebody else is out. Okay. What else has to happen in the problem? What's this do? Down 1. So on the graph paper, it's super simple. You just take each point and drop it down 1. So every one of your points that you plotted gets dropped down 1. On both sides. So the pink, I'm not even gonna erase the black this time, but the pink is the final answer. Okay, so we drew right, mirrored around the left, that's the absolute value part, and then we dropped it down 1. But look on the back side. Back side uses the same picture, so we'll do 1 from the back side. Which one would you like to do back here?
This one.
Which one?
We do 9.
9, yep. So what's happening with 9? It's actually got the same kind of concepts involved with it, but it's a very, very different problem. Okay? Very different. PEMDAS, we're gonna start in here, right? So what's that gonna do? That's gonna move everything left 1. So I'm gonna start with that. I'm gonna take everything left one. So every one of my points, 1, 2, 3, 4. And this is super simple. Once you get it started, it's easy. Here's my trapezoid, left one. There's a big triangle. There's my little triangle. So every point simply got shifted over left one of where it was originally. So 1, 2, 3, 4, this one started at -5. Everything went left one. Okay, now, this absolute value is different than the one we just did. The absolute value we just did was this one. Our last problem. See how it's different? This is an absolute value inside the problem. It's not the absolute value of the whole problem. When it's the absolute value of the whole problem, that is bottoms up. That's make it positive. So in other words, anything that's already positive is going to stay the same. So this positive means above the x-axis. So if it's above my arm, it's already positive. So it's not changing. So this part of the picture is going to stay exactly the same. But what's going to happen to this trapezoid now? He's getting flipped up. So this isn't a whole flip. This is a flip only of the negative parts. So this guy has to flip up too. If we wanted to flip the whole picture, then we would put a negative in front of the problem. A negative in front of the problem flips the whole thing. If we're absolute valuing, we only flip the bottom parts. Okay? All right, so that's a little bit of review to get us warmed up. Now, let's get our notes out and let's jump in. With 1.7. So 1.7 is word problems. And essentially, there are going to be 3 kinds of word problems that we are going to be emphasizing. So we'll talk about those. First, though, we have this little set of problems that kind of get us into word problem groove. How do you write mathematically 6 more than twice a number? How would you translate that into math? Right now it's English. How would we translate it into math? Wyatt?
2x plus 6.
2x plus 6. 6 more than twice a number. Now, if he used x, could he have used a different letter? Yes, that doesn't matter. So if you said 2n plus 6 or something, that's fine. It's also fine if you said 6 plus 2x. Could it be that way too? Yes. Okay. 6 less than 4 times a number. Now be careful with this one, Jack.
No, they said be careful.
Well, go ahead, jump in.
I said 4x minus 6. So
You're right. That's exactly right.
make me think.
That is 6 less than 4 times the number. It says that means take 4 times the number and then subtract 6. Right? Now, is that the same as this? Can I do this one in that order? No, no, no. That is wrong. That is wrong. That is 4x less than 6. Less than 6, or 6 less than, 6 less than means minus 6. So Jack was exactly right. That's perfect. Perfect. Okay. 24% of a number. How do we write 24%, the word 24%? How do we write that mathematically?
Or 24 over 100.
24 over 100 or 0.24. Normally we do decimals, a fraction would be fine, but normally we do decimals. So that's 24%. Now, of, what does the word of mean to the mathematician? Times. When we say 24% of something, we mean 24 times a number. So 0.24x is 24% of a number. 0.24n, 0.24y, doesn't matter. Okay? All of our percents, when it says 24%, we're gonna put that into the problem as a decimal, 0.24. Okay, D. I go to the store and I'm going to buy something that costs X, but there is a 15% discount and a 7% tax. So Izzy, you just went shopping last night, was anything on sale? Yes, of course it was, because we only buy stuff on sale, right? That's a smart thing to do, buy it on sale. Okay, or at Goodwill, whichever works your switch. Now, when you go to the cash register, let's say I bought this thing and it's $10. When I take it up to the cash register, if it's on sale, that comes off, right? But then I always have to pay tax and that goes on. So when we talk about price adjustments, I'm not gonna pay $10 for that thing. I'm gonna pay something else because they adjust the price. There are two ways we can adjust the price. We can take off an amount like we do for a discount, or we can add on an amount like we do for a tax or a tip or whatever, okay? Now, how we're gonna handle that, I know when you were in first year algebra, you did the problem in steps. We're not gonna do that. We're past that. We've got calculators. We are just going to do it in one step, and here's how it works. We're gonna take whatever the original price is, and that's X, and you're gonna multiply it by our adjustments. So I have two adjustments I am making. There is a 15% discount, so I'm gonna say minus 15%. And then there is an add-on that's 7% tax. Would you agree with that? So every adjustment, everything you're doing to that price is going to be another multiplication. The way you figure out what to multiply by is you start always with 100%. What is 100 minus 15? 0.85. And what is 100 plus 7? 1.07. So we take 100%, which is the number 1, and we either subtract the percent if it's a takeaway, or we add the percent if it's an add. Now, I can't really figure this out because I don't know what X is, but that's the strategy we're gonna use every time. So when we figure out what we're multiplying by, we start with 100, 100%, 1. And we subtract our percentage if it's a takeaway, and we add our percentage if it's an add. So 1 minus 0.85, 1 plus 0.07. That's what I multiply by.
So is the 7% before or after the discount?
Doesn't matter in this case,
Okay.
okay? It's gonna be after. Always, that's the way the cash register does it.
Oh,
They don't tax you for regular pay, right? Okay, E, my salary after a 7% raise. Okay, so here's my salary right now, okay? The principal walks in and says, oh, Lisa, you're doing a great job, we're gonna give you a 7% raise. What will I multiply by to adjust my salary? Now remember, we never multiply by the percent. It's always 1 plus the percent or 1 minus the percent. So what's a raise? Is a raise an add-on or a takeaway? Add-on. So it's gonna be 1 plus 0.07. So I would take whatever my salary is right now and multiply it by 1.07. Now, what if she came in and said, Lisa, you're doing terrible, we're gonna take away 7% of your salary? Then, what would I multiply by? 0.93, because remember, when you are adjusting a price, oh, my salary, whatever you're adjusting, you never multiply by the actual percent. You multiply by 1 plus it, if it's going up, or 1 minus it. So if she's gonna take away 7% of my salary, then it's 1 minus 0.07, 0.93 is what I multiply by. This eliminates all the round-off error that you have in multiple step problems. When you start multiplying and subtracting and multiplying and adding, you get some round-off error. This eliminates it. All right, let's skip number 7, F and G, and go down to 8. What is the final cost of an item whose original price is X, and there is a 20% discount and a 7% tax? So start with your original price, and soon we're gonna have some numbers here. We're actually gonna do some problems. But whatever that original price is, and we're gonna multiply it by 2 things, because we have a discount and we have a tax. Now, discounts are minuses, so we're gonna subtract 20%, and we're going to add 7%. Does that make sense to you? So when I multiply, it's gonna be 1 minus 20%. So 20% is 0.20. 1 minus 0.20 is 0.80. Listen, if you're struggling with this, stop a minute and think. If I take away 20% of the price, how much am I actually gonna pay? The other 80%, right? I'm paying 80%. Okay, and then I gotta pay tax, so that's gonna be 1 plus 7%, which is 1.07. Don't write 1.7, that happens a lot. 1.7 would be adding on 70%. Shoot, we don't want that. Right, that would be a lot. Okay, all right, so then let's go back. We're gonna do some of those in a second. Let's get F and G taken care of. We have a rectangle whose width is 3 less than its length. Okay, the width is 3 less than the length. Can you come up with mathematical expressions to describe these 2 sides? If the width is 3 less than the length.
The width could be like 5, and then the length could be 2. Oh no, the other way around.
The other way
The
around.
length.
Yeah, so those would be actual numbers. I'm thinking about, I have to write an equation from this. So what if I called my length X? What would my width be if it's 3 less than the length?
X minus 3.
That's what it said. Wouldn't this be X minus 3? So the width, or excuse me, the length I just said is X. Something has to be X. It doesn't matter. I'm picking X for my length. So then my width is going to be 3 less than that, according to the problem. Now, what's the area then?
Just multiply.
Just multiplying together. So this would be the area, X times X minus 3. Perfect. So first we have to come up with labels for our sides, and then we can find the area. All right, G. Our job is to find the perimeter of this rectangle, and the length is twice the width.
Well, the length would be 2x and the width would be 1x.
What do you think about that, you guys? Is that okay? Good? Now this time we want perimeter, so what does that mean? Perimeter means all around, right? So if that's an X, and this is a 2X, it's a rectangle. So we're gonna add them all up. So X plus perimeter equals X plus 2X plus X plus 2X. I think I can add those all up. So what's my perimeter?
6x.
6X. So with these two rectangle problems, we had to let something be X. And there's really no rule for that. You make X whatever it seems like it should be for you, and then figure out what the other dimension is, and then do your area perimeter. Good work. Okay? All right, let's look at number 2. Now we're actually gonna do some problems. All right, so your favorite teacher received a 3.2 salary increase. If her original salary was 1, 2, 3, 4, 5, so here's my salary right now. And they send me a letter that says, we're gonna give you a 3.2% increase. How will I find my new salary? Remember, if you're adjusting a price, or if you're adjusting a dollar amount, you're gonna multiply for each thing you're adjusting. Well, I'm only doing one thing. I'm getting a raise, which is a plus. I'm adding on. What am I gonna multiply by? 1.032. Why am I multiplying by 1.032? Because when I am adding on, it's 1 plus whatever I'm adding on. And decimally, don't get confused, 3% is 0.03, right? And it's 0.2 on the end, 3.2%. Move that decimal 2 places. So typing that in on my calculator, 1, 2, 3, 4, 5 times 1.032. I'm gonna be making $12,740.04. With money, make sure that you're rounding off to the nearest cent. Now this one worked out fine, but never put like another decimal point on the end of that. That doesn't make any sense with money.
You round up or down?
It
Or
depends.
just to the
If
nearest?
it's 5 or higher, you round up. This one didn't involve any rounding, though. This one came out just like that. All right, last year, a pre-cal book cost $89.50. This year, it costs $97.75. Find the percent of increase. Oh man, a little bit ago I mentioned first year algebra. This comes back. This is a first year algebra problem. Does anybody happen to remember how to find, actually it's the percent of change. It can be up or down. Does anybody remember how to find this, Jack?
Don't you put them both over 100 and cancel them out? Or is that a whole different thing?
That's a thing we do, but yeah, no, that's not what this is, but that's an idea.
Did you divide them?
It is, there's a little formula for it. It's the difference over the original. So it's the difference of the two numbers, so that means I'm gonna be subtracting them. So it's 97.75 minus 89.50 over the original, which is 89.50. Now, when you type this in, be sure 97.75 minus 89.50. Make sure you hit equals. After you type in your top, make sure you hit equals, and then divided by 89.50. I came up with 0.0922. That one needs rounded off, it goes on a long way. What is the percent then? It says, find the percent of increase. What percent did this book go up in price? 9.22%. There was a 9.22% increase. if the thing is going down, if the price is going down, you would calculate it exactly the same way, but it would be a decrease then, obviously. All right, try C on your own. Try C, you're buying a new car. 2, 3, 4, 5, 6. And then it went down to 18,765. Find the percent of decrease. Percent of any kind of change is found the same way, same way. Now, Jack is sitting here working out the math by hand. And that's exactly what's gonna happen to you if you don't have a calculator, okay? You gotta have a calculator every day. If you don't have one, then you're going to have to do the math by hand or miss the problem. I mean, that's it. And there's a time limit. You're not gonna have, if I give you a 2-problem quiz, you're not gonna have all period to do the math by hand. Bring your calculators. Is Sean, you listening to me? Okay. All right, so what anybody come up, anybody with a calculator come up with something?
19%, with 19.99%.
Well, actually, if I got 0.1999, so if I have to round that off, that's actually gonna be about 20%. You can't say 19.99 because there's a 9 that comes after that, so it would have to go up to 20. So that's a 20%. And this time, it is a decrease, right? We always wanna say whether it's a increase or decrease, and you'll know by looking at it.
Should we just write that out, or we put a negative?
Just say 20% decrease.
Question, so I'm gonna direct out 199.9. Then how do you move the decimal point over the one or two times?
Okay, so the decimal is 0.1999914734.
Yep.
So, 2 places, that makes it 19.9991474%. Nobody's gonna write all those decimal places, we normally round to the 100th. When I try to round to the 100th, what happens? There's a 9 after it, which means what's gonna happen? It's gonna round up.
You move to 100, because out of 100.
Got it. Okay. Let's see what's next. Okay. Now we have our box problem. Alright? Didn't we do these before? We've never done a box problem before.
Not in this one. Some of them.
The volume of a box.
No, yeah.
Didn't we ever take a piece of paper and cut out the corners of it? Alright, I need everybody to take out a piece of paper.
A blanket.
Yep, it doesn't matter, it can be any kind of, we're gonna rip it. So something you don't want, so either a brand new piece or a piece of paper that you don't care if it gets destroyed. So we're gonna take our piece of paper. Alright, so everybody hold up your paper, I wanna make sure everybody's got about the same size. Yeah, you're only using regular notebook paper, okay? For the same size as regular notebook paper. Alright, so here's what I want you to do. Each corner of your paper, each corner here, I want you to rip out a square. So tear a square out of each corner. Somebody do it. If I do it, everybody's gonna be the same size as me, and that's gonna ruin the point of the exercise. So yeah, that's what, right here, Mackenzie's got it. She ripped a square out. Now your square might be bigger or littler, But now you're gonna take that same size out of each corner. So you're gonna rip the same size square, whatever square you have, and we're not measuring, so just get as close as you can. Okay, just as close as you can.
I'm squinting to look arts and crafts. That was a good one.
All right,
Flames.
and when we're done, all of this is going in the recycle box, we're not gonna litter. Okay, once you got your corners all ripped out, then, see how you got like these flap things? Hold those flaps up. And you're gonna make a box. So go ahead and fold up your flaps. Yep, Leslie's got a box made. Nice little box. And I'm gonna grab your box, Leslie, and I'm gonna grab Wyatt's box.
I'm not good at
Okay. Let's see if we're having more boxes. Okay, so everybody's got a box. Now, usually we have a little bit more variety in our boxes. You guys are all thinking the same. But these are a little bit different. These are a little bit different. Does it make sense to you that depending on the size of the corners that you ripped out, that your box could be a different size than somebody else's box? Like it could be taller, smaller, flat, longer, and, you know, not as high. It all depends on what size corners you tear out, right? So let's suppose that I were really nice, and I had a giant bag of M&Ms, and I walked around the room, and I filled your boxes with M&Ms. Would everybody's box hold exactly the same number of M&Ms? No, because your boxes are different sizes. Now, we all started with the same size paper, but because we cut out different size corners, our boxes are different, and they hold different amounts. Okay? Now, don't you wanna be, I'm assuming you're all chocoholics like me, don't you wanna be the person that has the most M&Ms in your box? You want to build a box that holds more M&Ms than anybody else's. This is one of the big math problems in pre-calculus. Every kid in the whole world who takes pre-calculus is going to do this problem. We are going to do it with the calculator. The calculus students are going to do exactly the same problem, but they're going to do it using calculus methods without the calculator. It's maximization. We need to maximize the volume of our box, okay? So, set your box aside for a second. Here's our piece of paper that we're starting with in this problem. It's 12 by 14. Here's the paper. You took your scissors and cut out corners. True story, I did used to use scissors for this exercise until a boy cut a girl's hair and sat in front of him.
On
Yeah.
purpose?
Yeah, so no more scissors. Okay, now we rip.
And they were seniors?
It's hard to imagine, isn't it? Yeah,
No.
okay,
Cause I.
so this is the scenario. So you have cut these out. And so literally now, the piece of paper you looked at, after you cut out your corners, it looked like this, didn't it?
Yeah.
Yep. And then you folded these up. And these dashed lines are like where the creases were that you made. And you folded it up and you made your box. Now the problem is saying, what is the maximum volume of the box? Well, the box is what we call a rectangular solid. Does anybody remember how to find the volume, all those formulas you learned, anybody remember the one in geometry for rectangular solid? Volume equals length times
Width.
width times height. It's the easiest one of all, the easiest formula. Length times width times height. So I want you to look at your box for a second and imagine that this was the side of your paper that started out being 14. Is this now still 14? No, because you took off that net, right? We don't know how big those are, let's call them X. So how long is that box now? How long is this little dash line right here?
14 minus 2x.
Bingo! There's the length of your box, 14 minus 2x. 14 minus 2x. It was 14, you took off an x and an x. Subtracted it, 14 minus 2x. What about this one right here, this dimension of your box? 12 minus 2x. Didn't you do the same thing? Didn't you take off an x over here and an x over here? So it's not 12 anymore? It was 12 to start with. Then you cut those two pieces off. Then you folded up the flaps. So think about folding this flap up. What's the height of that box? How tall is that box? Isn't it just x? That's the height. Because the corner you ripped out becomes the height, doesn't it? When you fold it up. So here is the equation for the volume of your box. So part A says, write an equation for the volume of the box. Done. Now I want you to listen to me. This is not only going to be a test question, it's going to be on the semester exam. Okay? So, let's talk about this for a second. What if the paper had been, it's going to be exactly the same problem, but the paper is going to be a different size. So what if the paper is 16 by 30? What is going to change in the equation? 16 minus 2x, 30 minus 2x, x. That equation is never changing. Okay? So when we take our test, and then we wait December and take our exam, however big that paper is, all I'm gonna do is change the numbers, however big it is, first dimension minus 2x, second dimension minus 2x, x. That's gonna be the volume every single time. Okay? Now, the next question says, what's the domain? What do we mean by domain? Which variable are we concerned with when we talk about domain? X. So remember, what was x? X was the corners that you cut out of the paper, right? These were x big. I want you to think about this for a second. What is the smallest that x could be? 0. Exactly. X, this is going to be an interval, and I'm going to write it in inequality too, to get a feeling for it. X, the smallest is 0. Kids, can I say to you, rip out -1 inches? Can you do that? No. The smallest you could do would be rip nothing, 0. Okay. How about the biggest? Think about your piece of paper. Think about this piece of paper particularly, which was how big? 14 by 12. Think about that piece of paper. Could I rip out, could my x's be 100? No, the paper's not big enough, right? So what's the biggest, think about it now, what's the biggest I could rip off? 6. Why is 6 the biggest that I can rip off?
Because it's half a 12.
Because it's half a 12. Kids, your smallest dimension is 12. If you have to rip off a piece on each side, could you take 7 off each side? No, you only have 12, right? So could you take 5 off each side?
Yeah.
Sure. But you can't take more than 6 because you only have 12 and you're taking it off both sides. So where did this number come from? Where did this 6 come from? It's always half of the smallest dimension. Whatever your smallest dimension is, half of that is the biggest you can tear off. So back to my paper that was, I already erased it and I can't remember, but let's say it's 16 by 30. What would my domain be for that piece of paper?
0, 15.
0,
Oh,
8.
0 to 8. It's always half the smallest. Jared, I can take 15 off this side, but I can't take 15 off this side. So I have to look at the smallest dimension. So this is the interval notation that describes x is between 0 and 6 in this problem. Okay? Next question. Find the maximum volume. Okay, so now we're gonna find the maximum volume. So what I'm gonna do is 2 things. I'm gonna go to y equals, because I'm gonna graph this. And I'm gonna type in this equation exactly the way I wrote it. So you do not have to multiply it out. You can leave the parentheses. So parentheses 14 minus 2x, parentheses 12 minus 2x, and x. So I'm typing in my equation exactly the way I wrote it. All right? Then I'm going to window, and this is hugely important. I hope you're taking good notes. Go to window. And when you go to window, it asks you some questions. It says x min, x max, y min, y max. Okay? Now, right here, you've done x min and x max. You have told me right now, by saying this is the domain, that x has to be between 0 and 6. Now, what about y? Well, in our equation, I put a v here, but that's really your y, right? So y stands for the volume. Think about a box. What is the smallest volume that a box could have? 0. Can it have a negative volume? So 0 would be the smallest. So y min is always going to be 0. It's a volume. Isn't this guy right here what you're looking for? So what we're going to do is we're just going to pick a number and throw it in there and see how close we got. Okay? So I'm going to pick, how big is my paper? I'm going to pick 200. So let's just pick 200. Put it in there. You're going to see what happens here in a minute. Just relax. Pick a number. All right, now hit graph. And here is what you have to see. When you hit graph, you have to see some kind of a hill. Okay? Got it, okay? Now I want to show you something. Let's suppose when I said pick a number, you picked 100. All right, let's go back to window, change your Y max to 100, hit graph, and what happened?
it's off the screen.
It's off the screen. So remember, when you do your Y max, you are just guessing. Every time I do it, every time you do it, we're gonna guess. If this happens, then you need to go back and guess bigger. Now, my first guess was okay, but it usually isn't. But my first one was okay. I see my hill. If I don't see my hill, then I need to go back, guess again. Because this right here is the answer to the question. Isn't that the maximum? The highest point? Right? So here we go. This is what we're gonna do. Oh wait, I gotta change my window back. Get my graph. Okay. All right. So everybody's got this, right? Okay, if you don't, you're just gonna have to pay attention because we're not going back through it. We're gonna do another one. Here we go. Got this one? Yeah, some of you have this anyway. All right, write down these steps unless you've done this before and you can remember. To find the maximum, we press second, and it's this button right here. It says trace, but above it is calc, and that's the button we want. So second, calc. In that list of options, do you see maximum? So we're gonna pick it. And now the calculator's talking to me. It says, what is your left bound? So you have a cursor, move it over here somewhere. So just use your arrow button and move your cursor so it's over here to the left, anywhere to the left of the point you're looking for, and press enter. Now the calculator says, okay, what's your right bound? Well, move that cursor so it's over here, anywhere over here, and press enter. Then simply move your cursor till it's somewhere in this vicinity. It doesn't have to be exact, just somewhere in this vicinity, and press enter. And at the bottom of the screen, it says x equals I'm gonna round to the nearest hundredth, so 2.15 and 160.58. That's what my screen says, right on the screen. Anybody else get those numbers? Okay, so what does that mean? That means that at your maximum, your x-coordinate is 2.15 and your y-coordinate is 160.58. That's the coordinates of the maximum point. What were we trying to find? What was the answer, or what was the question? Find the maximum volume. Which of these numbers, the x or the y, is the volume? Y. Because when we wrote our equation, didn't we have y here? So the maximum volume of the box is 160.58 cubic inches. Volume is cube, inches, inches, inches. Now what about this x? What does that represent? What did x stand for in our problem?
The height.
Well, the size of the corners that you ripped out, that became the height of the box, but it started as the size of the corners. So remember when we were talking about being gluttons and building the biggest box we could to hold the most M&Ms? What size corners should we have cut out of this paper? 2.15 inches. So sometimes the problem will say, how big should the corners be? And then this would be the answer. Our question said, what is the volume? So that was the answer. Okay? All right, well, we didn't have time to do the second one. We'll do the other one next time. 1.6 homework has been assigned. So look in Power School, look in Schoology.
It says it's due Monday, is that correct?
Is that what it says? Whatever it says is accurate. So with that, right.
I was listening to a video about really school and then out of nowhere just snaps and it's like, none of your music is good. Literally listen to it.
If you did not get your picture to graph, you can bring your calculator up to me.